of Troy, and let me see if it works this way. Sorry, yeah, I will just use my mouse. So the Laboratory of Computer Science of Troy and Orange Research. And my academic supervisors are Philippe Lacombe, Caroline Prodon, and on the industrial side, we have Yann Dujardin and Eric Courtin. And since this PhD is also rooted in industry, one of the questions we ask is how can we solve quantum computers if one day we have to introduce quantum computers in some company? And so we try to start an answer to this question, and today I will show a part of the answer. So the outline is as follows. First, we will look at what kind of physics we are dealing with when we talk about variational quantum photonics. Then we'll see what's photonic implementation of quantum circuits. So then we can talk about one variational method, because there are other ways to do it, and then a toy use case solved on a simulator. So to start with, to get back to the quantum computing landscape, as you can see in this nice map from the Quantum Insider, it's a very fertile market for quantum vendors. And some of the attendants here can see their companies there. And the question is, which quantum computer should we use and for what application? So in this talk, we are here, we're in the photonics, so one technology in particular, and Candela, it's discrete variable photonics, as opposed to Orca or to Xanadu, who are other photonics, but they use another other physics principle. Now, why photonics? Because since we have only a few number of commercially available quantum vendors, then let's just brute force and have a toy case. We solve it in the different commercial quantum computers and compare. All right, so the question is easy to ask, but quite difficult to answer. Which quantum computer for which problem? As you can see here, we might have some leads, but once again, our lifespan is limited, so we have to pick some. And photons, this is the claim, offer an interesting platform for quantum information processing. We've saw this with quantum communication, with cryptography, so why not in quantum computing? And there are three reasons to that, or three arguments. The first one is less errors because of the nature of these particles. So we have minimal decoherence, high fidelity transmission. We have integration with the state-of-the-art optical fibers technology and communication technology. So we can think about good scaling. And then there are several ways to encode a qubit in photons, which is also an interesting lead. So what kind of physics we are dealing with? Yesterday we had a very nice presentation about VQE, also on Candela, and we were talking about fermions. Today we are talking about bosons. So some people have collection of insects or cars. Here we have the collections of particles, and the bosons are our photons. They have one difference with the fermions is that the associated wave function of the particle is symmetric, and this symmetry does what we call this piling up phenomenon. So in electrons, you've probably heard of Pauli exclusion principle, that two electrons cannot be on the same spot, on the same mode. In photons, it's the other way around because they are indistinguishable. And this will be very helpful in what's coming next. And so the physics we are using here is the physics of second quantization. It was already introduced yesterday. We are using what we call annihilation and creation operators, and we are acting on a quantum state that is described this way. So this looks like a ket, but it's not a ket, it's a Fock state. And the Fock state tell me how many, because those are integers, how many bosons, in my case photons, do I have in some mode. You saw yesterday in the presentation that we had electrons, so we could always have at most n equals 1. N equals 1 or n equals 0. We will see that with the bosons we can have more than that. So we are working in a Fock space. we will see that a Fock space is bigger than a Hilbert space. So this is another motivation. If we have a bigger space, then we can encode more data, so we can do stuff. But we put under the carpet barren plateau and the vanishing gradients for the moment. And here is an example. So let's define the usual ket zeros that we are used to. It's a column vector. But actually here it says that we have no photons in mode 1, no photons in mode 2, whatever mode mean. For the moment, bear with me. We will see what is a mode. And now I'm going to apply a creation operator that's here. So I'm just going blindlessly apply this rule. So then I can have, I create one electron, big mistake, one photon in mode 1. You see the one appearing here. And then I apply another creation. Then I create the second photon in the second mode. All right. So why I'm saying this? Because I would like to emphasize the difference between discrete variable photonics and continuous variable photonics. Discrete variable photonics, we are working, we can get back to a Hilbert space. So it's a Fock space, but then we encode qubits, so we get back to a Hilbert space. We either detect or not a photon. We send a single photon at a time, and we use this for universal gates. So we can implement the same gates you saw during the tutorials, during the talks, NOT gates, etc., but they are implemented differently with optical components, as opposed to continuous variable used, for example, with Xanadu or PsiQuantum. And they use completely different physics for this, so it's more suitable for communication or for other tasks of sampling. So this we are not covering here. All right. We can just skip this fancy formula and look at here, and then we can get back to it later. My point is, here, I have a Fock state, so this is a quantum state. And what does it say? It says that I have 2 photons in mode 1, I have 0 photons in mode 2. Here I have 1, 1, and so on. The problem with that is that not all Fock states are qubits. So I need a mapping to make my Fock state a qubit. And one mainstream mapping is called the dual rail encoding. For now, it means that we have a 1 appearing in one of the modes. We will see it here. The dual rail encoding, so I was telling you, bear with me, a mode, so a boson in a mode. One very easy way to think about it is the optical fiber. You send you send data through it with you send a signal. So now think about sending a photon in some waveguide. This waveguide is here, is a path. So this representation is a representation of a qubit with photons. Why? Because I'm sending a photon, and the photon can be either in the first or in the second waveguide. This is what we call dual rail encoding, and here the mode is a path, is where we are sending the photon. There are other ways to encode qubits, for example, polarization, we are not going to cover here. And finally, now that we have a notion of quantum state that we can map to a qubit state, we can introduce the notion of unitary that is going to be our gates. And the unitaries here are compositions of optical components. The optical components we use are called beam splitters and phase shifters. And the composition of these is compositions of operators, and it can give us a universal quantum circuit. And if we have a universal quantum circuit, in theory, we could implement any quantum algorithm we want. In theory, I insist. And so now we have all the ingredients to be able to design a circuit that will work under some variational principle, meaning that we are going to fine-tune some parameters such that we are minimizing some Hamiltonian. All right, so this approach is proposed by Orca Computing. They are continuous variable photonics, and it was in 2021. So for a given set of parameters, what are these parameters? They are the value of the components we just mentioned, the beam splitters and the phase shifters. We are going to produce quantum state. It means that we are going to do some measurement, And this measurement, as I said, it has a lot of quantum state. It's not necessarily a qubit. We are going to map them to bit strings. And then those bit strings, we will use them to evaluate our cost function. Our cost function, if we remember, is the Hamiltonian that encodes, usually QUBO, but we can do something else. And then we measure the energy, and we give the output to a classical optimizer, preferably a gradient-free method, such that we are optimizing the parameter. We are looking for the parameter for which the energy is in the ground state. So it is a variational principle. And to do this, to do a variational principle, of course, we need an ansatz. And the ansatz here is a composition, again, of beam splitters and phase shifter put in some way. And here, this is Perceval. It's the it's a Python library that implements Candela technology. So this ansatz here, yesterday you saw a meaningful ansatz, excitation states. This is a generic ansatz. It doesn't take into account the reality of the Hamiltonian. And so the workflow goes as follows. I have a set of parameters, so the parameters of my components here that represent an ansatz. And then I measure, so I start with some random or not too random initialization. I have some fog states. Fog states are not necessarily qubits. One technique to go is to map these to bit strings. The mapping is with parity mapping. We can talk about it later. And then we have a loss function and a classical optimizer. So a use case is to have a Hamiltonian that describes an operation research problem. And in our case, we have, so it's the minimal multi-cut. It's the generalization of the min cut, but spoiler alert, we solved the min cut, not this one. So in general, in Orange at least, we are interested in problems that can encapsulate cybersecurity attack scenario, where we have what we call sources, so the nodes named S, and we have sinks, the node named T, and we say that we have some attack, someone getting to the network from S and trying to go to the associated T. So this problem, as presented here, is still solvable in polynomial time because we can apply twice, we can solve it twice as a min cut, but as soon as we have three pairs of terminals, so S1T1, S2T2, S3T3, the problem becomes NP hard. And yeah, so the idea is, let's have a look at what quantum can do. In this case here, if we want to isolate S1 from T1 and S2 from T2 with the minimum cost, the edges we should remove are, are the edges here and there. So as I said, this problem, okay, the optimization problem is NP hard. Even the decision problem associated to it lies here in NP, and the hope is that maybe if bounded quantum, so BQP, bounded quantum probability algorithms are near this class, maybe we could have some chance and solve it. And yeah, so to do so, it's pretty straightforward. This is the most explicit, naive implementation of the min multicut. We are minimizing the weight of the edges we remove, being xe equals 1, such that for every path between S and T, we are removing at least one edge. This is an exponential way to express this constraint. Usually, classically, we would use approximate algorithms or maybe try to hybrid it with some flow algorithms, which is not the case here. And this becomes very easily a QUBO following a Glover method or a quadratic penalization, as we put all of our constraints here, some sort of augmented Lagrangian, and then we have a penalty that is large enough to penalize us whenever we violate the constraint. So we have to add what we call slack variables to make this inequality, and that scales very poorly we don't even need to run tests to say that it scales poorly. So one approach to go is that to say, okay, let's just ignore these slag variables. Let's try to express it differently. We have some leads, but it never does as good as a classical approach. And so here we, as I said, we solved the min cut. I will show you one. Okay, not yet. This is a very quick, but important reminder. Why do we always say QUBO? Because QUBO is isomorphic to the Ising Hamiltonian. It means that we have two interactions at most. So we have xi, xj, and this is easily mapped to the Pauli matrices Z here, such that we are solving an eigen problem. So we are looking for the eigenvalue associated to the minimum eigenstate, which is the minimum energy of our Hamiltonian. So, but we could have done differently, of course. It depends on which Hamiltonian, or how good the Hamiltonian is in capturing the optimization problem. So here is, So here is a very quick, I meant a small toy case example. So this is a min cut, polynomial time solvable, brute force solvable, very easy, but it's more of a preliminary result. So quick reminder of the QUBO without the slag variables when expanded. This is our Hamiltonian. We do the workflow we mentioned. So we map, we initialize the parameters, we map the parity to bit strings, we evaluate, and then we see that of course, either for simulator or for real QPU, for this small toy case, we reach optimality for 4 variables. As soon as we get to 7 variables on simulator, it gets complicated without GPU because we are using the SLOS backend. So it simulates the whole vector state, so we can see how it evolves. And when we use real QPU for this particular Hamiltonian and for this way of encoding the bit strings, we have an optimality gap of 30% at least because of the noise being the detection of the photons or not by the detectors. And so a future work to that is noise characterization. Try to say or try to see how the noise would impact our workflow. Trying advanced algorithm, this is what Candela is doing right now. They are doing the CVAR VQE, where they focus on the tail of the probability distribution that we get from the sampler. The hardware acceleration is for simulation purpose, so then we can try more than 10 variables because it's very non-representative for the moment. And then ideally, I didn't mention it here, having ansatz-aware interferometers, so the compositions of beam splitters and phase shifter, somehow trying to map our Hamiltonian to this. And finally, just one remark concerning QDIT, because they were mentioned yesterday. A QDIT is a many-level system as opposed to qubit, where we have only 2 levels. What they do in Candela with Perceval is that they use the QDIT logic but on qubits, because of course experimentally they do not have qubits, not for the moment. And the idea is that we can have a better compressed circuit, so maybe less beam splitters, less phase shifters, and maybe even less modes when we encode our problem using the QDIT logic. So this is also another perspective of work. Thank you very much for your attention.
Ali, are there questions? Yes. I will move here.
Thanks, Ali, for the nice talk. Is there any reason why you chose binary optimization problem? Because in photonics, what you have is Q modes, so you can have higher energy levels. So it is better to encode in Q modes, like problems like integer optimization or mixed integer or continuous variable optimization, which if you, in the language of, when solve it on other platforms, we translate it into qubits because it is a limitation of the hardware. But here you have an advantage where the photonic can give you this Q modes, and any reason you targeted binary optimization?
Thanks for your question. Twofold to answer. The first one is, since we are doing operation research applied to industry, at least in my case, most of the time it boils down to discrete optimization. So binary actually is what I'm looking for. And then for Q mode, at least with path encoding, so the dual rail I showed, sending a photon in two rails, and it's either on the first, either in the top or in the bottom. Here in this case scenario, we do not have Q modes. They are more generally used, to the best of my knowledge, in continuous variable photonic computers, such that the ones from Xanadu, to which they have a nice library, Penny Lane. And yeah, so some work was explored there, but not taking into account the hardware specifics, just implementing QUBO, for example, or any other algorithm on their simulator that is run on photonics, but using continuous variable physics, photonics physics, yeah.
One other question, I guess, in your case, the gates are more probabilistic, so you have to run it multiple times, right? Any comments on the measurement overhead? How much, how many times you?
Yeah, so for the measurement overheads, at least in this approach proposed by Orca and we implemented here, we would need to measure, okay, let me show you this. It's smaller than what I thought. Can I zoom in? Oh, cool. All right. So yeah, when we measure, we get some fog state that is an optical state that says, oh, we have 3 photons in mode 1, so in the first rail, 0 photons in the second rail, 1 photon in the fourth rail, and 0 photon in the last. So it's more of a mathematical question, I guess, is when I do this parity mapping, when I parity map, so I say that odd numbers will be 1s and even numbers would be 0s, I'm packing several optical states into one bit string. So one question would be, how much of packing I need? Am I going to have a complete representation of my bit strings? Can I pick only interesting bit strings? And here, maybe there is the question of measurements. Maybe I need several measurements so that I can cover the whole space of a representation of my bit strings, which is yet under study. But yeah, so this is one way to think about the overhead. The other way maybe would be when you try to implement a controlled gate, which is complicated, and I think there will be a talk about it. In photonics, it's probabilistic, it's not deterministic, and there is an overhead for post-processing. So 2 ways to look at it.
Thank you.
Yeah, so I was curious, how did you determine the lambda penalty value that you used?
Yeah, so as we say in French, it's like cooking. So it really depends on the problem. It's how you want your spices. The easiest way to, the most reasonable way to say is that if you violate once the constraint, it counts as you violated everything. So you would have the sum, at least it's bigger than the sum of all of the weights of the action you are doing. And in this case in particular, yes, it is the sum of the weights of the graph. But this is one way of going about it. Suppose that you have several constraints and you are putting them in your function. Maybe some constraints are softer than the others. Maybe you have hard constraints, then you would have different penalties for different constraints. It's highly problem specific, but yeah, to my knowledge, of course.
Yeah, so thank you for the talk. I think in slide 9, you explained the difference between 2 different kinds of photonic computers. I didn't really understand it. Can you explain, not in detail, but a bit on their differences?
Okay, let me have a try, and if it's still confusing, we can talk about it later. So in In discrete variables, what we are doing, we have a photon source, and we send photon in some frequency, so maybe 1 every second or something, and then we send it in a waveguide. You can think about it as a path, and this waveguide at the end there is a detector. So when I send my photon, it's either detected or not, right? This is discrete variable photonics because we are counting the number of photons detected. So my Fock state, for example, here would be the detector in above detected 2 photons, the other detected none. And we can do the stuff we've done here. In continuous variable, it's about boson sampling, which is completely different paradigm. And as a general idea, in our case, we are limited to a finite dimensional space. In their case, it's infinite dimensional space. In their case, they use a lot of integrals because continuous, of course, and it's used for quantum communication in general. So there is one application, but I'm not yet qualified to talk about it because I saw it in summer school, solving different PDEs, so partial differential equations, that are close to the PDEs of a heat function, if you know. And then they would use some linearization, what they call Schrödingerization. It's done by Nana Liu from Shanghai University, and they need to use the continuous variable because the integrals are very convenient in dealing with the differential equations they are working with. In our case, I'm not saying that it's excluded that we will be doing operation research on CV, on continuous variable, but for the moment, when you do DV, discrete variable, you have to take care of what components you are using, what's the value of the beam splitter, etc. But when you do the CV, it's like in classical, you don't really care about the transistor you are using. You just have, it's like in superconducting qubit, at least in my case, I don't know how IBM really implement their NOT gate. I don't really care. But for discrete variable, you have to care, and maybe you have to find some cool way to map it to your Fock state, for example.
Okay, thank you. Perfect.
Thank you. Other questions for the speaker? No, I think we can thank him again. Thank you, Ali. And we have the last speaker. Mal. Oops. Let me check. For instance. Martin.
Yes.
You're going to speak?
I've got the document.
Where is it? No.
Maybe inside the site.
Ah, oui.
That's your.
Martin is going to introduce this topic on photonic quantum computing.
Yeah.
So thank you, Martin.
Hello, can you hear me?
Yes.
Okay.